Alrighty, so what we've got set up here today is a little experiment. We are going to overspeed this motor, we're going to overclock it. So we're going to see what happens when you go super synchronous, in other words over 50 Hertz. So here's our motor, here's our drive. For a reference, we are using a 4 to 20 milliamp source, a loop calibrator. And I've got a voltmeter across the output. So this places a 500 ohm burn-in across these two terminals. So the 4 milliamps across the 500 ohms is giving us that voltage. Okay. So here's our on-off switch. So this is providing, this is battery powered, and this provides the current for the 4 to 20 milliamp source. So this is sourcing the current. If it were a loop powered device, the supply would have to come from elsewhere. That would be a two-wire system in the case of a pressure sensor. So what we're going to do is start it over here. Now put it set up. And that over there is our hertz. So at 4 milliamps, running at 34 hertz. So I'm going to go up in steps of 25%. In other words, 4 milliamps at a time. And let's see what effect that has on the motor. We need that over there. The banana for scale. Alright. Let's put it over there. Don't let it in the way. There we go. You can see what size motor we've got. Good. Very important that we do these things. So let's go up to 8 milliamps. So there we're already at 123 Hertz. Okay. That's a 4-pole motor. So we are already running at over 3000 RPM. We're running at, that would be, yeah, I can work it out. Motor RPM, never mind, we're here to concentrate on other stuff. What happens if you overspeed it? So let's go up to 12 milliamps. There you can see the voltage come up, and you heard that increase in speed. We're now at 200 Hertz. Now what is happening is that we're currently running in the constant power region, so the voltage has stopped going up beyond 200 volts, which is what we're feeding this with. Only the frequency is increasing, so we're in the field weakening region. So the speed's increasing and the torque is decreasing. So let's keep going. And there we are, going pretty fast. That's 300 Hertz. 300 divided by 50 is 6. So 6 times 1500. So we're doing close to 10,000 RPM. Going pretty fast. Now we're at 400 Hertz. And you can hear the motor slowing down. You can hear it desynchronizing there. So there's actually not enough torque available to go any faster when you do that. So what happens is you just stall the motor. So there's very little torque being produced at this moment. The friction in the bearings and the windage losses is actually causing it to stop. So there you can see not much is happening. So let's go down again. And speeding up again. And then at 200 Hertz we produced enough torque to get it back up to speed. Now the other reason for that is the reactance in the rotor. Because your rotating magnetic field is cutting through the rotor bars to high frequency, the reactance increases, your rotor current decreases, that magnetic field decreases, and you further lose your torque. So that's why as the frequency came down and the motor started speeding up, you heard it suddenly accelerate. Let's do that again. So I'm going to take it back up to 20, and that comes to a standstill. And then I'm going to take it back down to 200 Hertz, and you'll hear it happen. That shot's quite hot when you do that. Come, slow down. Okay, that's enough. Right, back down. Hear it slowly accelerating. Yep, and there it goes. That's the reactance in the rotor. It decreases, your torque increases, and suddenly the motor accelerates back to synchronous speed, or the rotating magnetic field minus a slip. Okay, and then bring it to a standstill. So if I were to suddenly accelerate it at this point, you'd also see that phenomenon. Not so much. And it just smoothly accelerates. Alright, so basically when you can overspeed these by running them super synchronous. However, after 50 Hertz you get no more power. The power doesn't increase. So the torque decreases. So your system has got to be designed to be able to run at super synchronous speed with the torque available at super synchronous speed. So in other words, if you're going to do that, you may have to increase your kilowatt rating of your motor and drive over what you've got, over what you need at 50 Hertz. It also depends on the type of load. If it's a linear load, it's not so much of a problem with, but with a quadratic load, you're going to have a problem, because your power demand increases exponentially and your torque is decreasing. So generally, if you've got the power, you can go about 5-10 Hertz over base speed with a quadratic or load, a square law load. But that's it. You can't go beyond that, but you can go up to about 25 Hertz, 50% over base speed, a super synchronous, fairly safely, without performance problems and so on with a linear load. And it's quite common to do that. But does the motor explode? Did bad things happen? No, nothing happens. As you saw, it just stalls out. So that is it. Turn this off, and that is going to wrap it up for this little video. Something different. I was thinking about it today, and I don't think I've done a video like this, so I've set it up for you, and we've done the demonstration. Do you blow motor up by running it super synchronous? I hope I don't get in trouble for saying that. The answer is no, but there are considerations. So ladies and gentlemen, take care, have an awesome day further. I'll see you next time for more awesome stuff. Alrighty, bye.